Hi, I'm Dave Robinson, and welcome to another one of my screencasts where I'll be using R in RStudio to analyze data that I've never seen before. So as usual, this dataset comes from the Tidy Tuesday project, which is an amazing project run by the R for Data Science online learning community. And every week they release a new dataset, and let's see what data I'm going to be analyzing this time. Looks like the newest one is called Car Fuel Economy. Big MT cars. All right, so MT cars, people who don't know, is a classic data set. Classic is one word for it, of data that comes from the EPA, and it's MT cars originally is a data set often used for examples in statistical analyses, and it's a data set of cars, their weight, and how many miles per gallon they get. And it's used a lot. I'll actually show it quickly. It's built into R, so it's really easy to use in an example. And it shows 32 cars, miles per gallon, number of cylinders, displacement is I think the volume of the engine, and so on. So it looks like this one is going to be a much bigger and more updated version of that. So that sounds cool. I don't drive myself, so I'm actually not really knowledgeable about cars, but I'm looking forward to finding out what I can from this big MT cars data set. So let's get started. As usual, I start with library tidyverse, and I usually do theme set theme light. It's a semi-ggplot2 theme. I'm going to save this as car economy under in my Git repo. All right, and I'm going to read in the data set. Big EPA cars. Some parsing failures, but oh wow, it's much bigger than MT cars is. I'm going to pipe it to view. All right. Oh boy. Look at all these things. Barrels charge city co. It's not a very clean version, which is okay. I can start figuring out how it works. Cylinders, we've seen those for I'm guessing this is displacement of the volume of the engine. What type of drive it is. Each engine has an ID, a description which looks like it's something categorical, an FE score, several categorical variables like fuel type, highway. I really don't know what any of these mean. Highway 08U. Gonna have to, let's see, lots of zeros, so I don't know what, there's 41,000 entries, okay. I'm definitely not gonna use all these variables. I'm gonna use some of them, not others. And PHEV blended, okay. Data dictionary can be found at fueleconomy.gov. Cool. Here we go. All right. And let's see, is it in the same order? Not quite. This is alphabetical. I wonder, can I put these in alphabetical order? Okay, I guess I can. What I'm going to do is quickly say big EPA cars alphabetical, just so I can look at it. I don't know of a way to do this using... Oh, I guess I do. What I'm going to do is say, using the tidyverse, so we're going to say, I believe select can take a vector of call names. So I'm going to say sort call names big EPA cars, and now I've selected them. Look at that, alphabetical order, starting with ATV type, going on to barrels 08, and so on. All right, just I liked having that. Type of alternative fuel or advanced technology vehicle. Okay, I do a lot of counting when I work with data like this. So if I took this data and I said count ATV type, and mostly missing, sometimes FFE, diesel, hybrid, etc. Okay. Annual petroleum consumption in barrels for fuel type 1 and fuel type 2. I'm definitely not going to use all of these unless I probably will. I'm probably going to fit a machine learning model. Okay. Cylinders, let's see. And what's the thing I'm trying to predict? I'm trying to predict the efficiency. Tons and tons and tons of variables here. Per gallon. Fuel price. No, I'm looking at vehicle is the one I'm looking at. Where is like the name of the car, by the way? If I look at this like big EPA cars view, do I see the name of the cars anywhere? Oh. Is it model? Okay, make and model, but it's not unique. So, oh, I got my ID here. Okay, where's ID? Vehicle record ID, model name, has MPG data. Okay, do I want to download the MPG data? I'm not sure. Let's see, modified on, start, stop. Okay, I'm still kind of just like feeling my way through this. Controlling consumption, barrel, see, mostly 0, don't know what that's going to do. City MPG, oh, okay. So one thing this has that I now understand is like there are variations on how we would represent fuel efficiency. A common one is city. So city 08. This is miles per gallon for. Wonder what all these are. Fuel type 1 for dual fuel vehicles. This would be the conventional fuel. Okay. I see. There's fuel type. Fuel type 1. Do we have a fuel type 2? I don't see one. All right. I'm wondering how common the dual fuel ones are. If that's going to make our analysis more complicated. So the story here that I was trying to say is that City 08 represents, here it is, the city miles per gallon. So generally, in my understanding, the city you're starting and stopping a lot, so generally the fuel efficiency is lower. Let's see. City MPG. The U's just mean unrounded. A08 means for fuel type 2. I wonder how many have a fuel type 2. Let's find out. Actually, I'll just do count city A08 greater than 0. Only around 1,000 have a fuel type 2. Maybe we start by ignoring those. I think that sounds kind of plausible. We have this many observations. I'm definitely going to be making some graphs in a second, but I also I'm thinking about what I might predict, and I'm kind of interested in predicting the city MPG. Do we have like a rural MPG or highway MPG? Here we go. Highway 08. So what I could do is take your big EPA cars, select city 08, highway 08, make model, and like there I'm starting to like pull in my own data set with like a smaller number of factors that affect it. Cylinders, displacement, drive, engine ID, engine description. Sounds kind of interesting. All right, so we can see like here we go. Between these two, this is a much more efficient city car. The Alfa Romeo Spider. I really don't know cars, but we can see, this is the engine description is a Guzzler. It gets only 9 miles or 14. How many engine descriptions are there? Notice I jump around a lot. I kind of have what I'd call like, I don't know what I call it, soft eyes when I'm looking at a data set like this. I find things that are interesting and I like kind of mentally jump to them. That's too many categories, but how about drive? Fewer. Okay, the reason I want to know how many there were is I've got a question already in mind. How does do highway and city fuel efficiencies relate? So I have two questions about that. One is which is higher efficiency. I have the suspicion that generally highways are more efficient than cities. Looks like that's the case for the ones that I'm seeing so far, but it's not always quite the same relationship. I can see a slight correlation just among these 10 observations that this is a Guzzler and has low efficiency in both. But whenever I compare two variables, I'm gonna use a scatter plot. So I'm gonna take this. I'm gonna ggplot to do city 08. Let's do city 08. No, let's do highway on the x-axis. Highway 08 to city 08. Geome point. I suspect there's going to be a correlation. Maybe there'll be some extreme outliers. Let's find out. That's actually a way higher correlation than I originally expected. I'm also kind of amazed at how high these efficiencies can go. Some can get 125, 150 on the gallon. I wonder if those are electric cars. I'm starting to suspect that, or rather hybrids, I should say. I'm going to guess that's the case. But no matter what, we can see is there's definitely a correlation. I can throw in, I mentioned my understanding that city efficiency is lower than highway efficiency. So I can throw an AB line at x equals y. It's going to show that everything lies under that AB line. Not everything. Aha! This is kind of neat. Okay, I'm now again, I am not a driver, but remembering something I heard, which is that electric cars, when you hit the brakes, actually use that to recharge the batteries. Like use the there's a engineering term for it. I don't remember what it is, but they use the car slowing down they gather some of the electricity from that, and that means some can actually have higher efficiency in the city than on the highway, and that's what makes me suspect these are your hybrids or your or maybe, yeah, I'm guessing your hybrids, not electric cars. How can I find out which of them are hybrids or electric? Electricity consumption, electric motor. Ooh, fuel type 2, let me see. Big EPA cars. Type 2. No, I never have a fuel type 2. That's a little bit odd. Maybe this data set is only single fuel type vehicles? Huh. If I say filter, no, that can't be right, because I see I got we have a column for that. City, where is it? I think it was city A08. Yeah, so I can say filter city A08 is greater than 0, and we do have 1600. But even among these, fuel type 2, always an A. Oh, well, that's frustrating. All right, let's see. Do any have a, I'm going to look for the word electric. Highway electricity consumption. Okay. I'm going to say how many of these have highway E? So a couple hundred have an electricity consumption. What about, is there a city E for city electricity? Yes, yep, the same number. Okay, and that means that we can add a quick column. I'm going to add in is electric, and it's going to be highway E greater than 0. Or I'm going to call it hybrid uses electricity. I'm keeping it kind of vague for now. I don't know that it's electric versus hybrid, but I know that it uses electricity if its highway electricity consumption is greater than 0. So what I'm going to do then is throw in that as a color. There it is. The ones that use electricity, this is exactly what I was expecting. The ones that are up here that have really high fuel efficiency, like a lot of miles per gallon, they have they are the electric cars, or at least the hybrid ones. I think it's such a big effect. I'm going to change this to be uses electricity, doesn't use electricity. If else is handy for creating these really helpful values in columns. So again, then uses electricity. I'm going to facet by it, and I'll separate them. That is, let them be on their own scales. All right, so this is what we're seeing. There's a tight correlation between highway and city efficiency. they're on very different scales in general. I'm also going to expand limits y equals 0 and x equals 0. So I'm going to say, I just think it's easier to tell a correlation there and tell relative amounts. Okay, so there are some hybrid cars that have relatively low efficiency, but mostly here we go. We got our I'm going to polish this graph because I like it. I'm going to say x is highway miles mpg, y is city mpg. Title: how does fuel efficiency differ between city and highway? And here we go. This gives us a couple conclusions. One is that it shows the distribution of fuel efficiency ranges from about 10 miles a gallon to 60 among non-electric cars, and more from 20 to 120 among cars that do have an electric component. That's good. And let me see. That's the first thing we find. We secondly find there is a tight correlation between your highway miles per gallon and your city miles per gallon. That makes complete sense. And we know that city miles per gallon, city fuel efficiency is usually lower than highway for non-electric cars, and is actually often higher for cars that use electricity in the city than on the highway. So that's some of the things we learned from this graph. All right. I'm going to move on to some of the other columns. That was just looking at our some of the variables we're most interested in predicting, like the fuel efficiency. Now you might want to use some of these predictors. So I did a select earlier, and I forgot what I selected. I'm going to go up until I find it. Here we go. Engine description, okay. Descriptor, I wonder what this is. Lots and lots of descriptions of types of engines. Probably a few too many in this case. What's a Guzzler? Vehicle subject to gas guzzler tax due to low fuel economy. I bet those are going to be at the lower end. Makes sense. All right. What other things can I use a predictor that are like this? Some of the simpler ones. We're looking at range, transmission descriptor, okay. Vehicle size class. Count V class. Cool. We have 34 types here. 34 is certainly too many, but it would be cool to look at the distribution. All right, now that we know there's a tight correlation between city and highway MPG, I'm going to use just highway miles per gallon from now on. You know what? I live in the city. I'm just going to use city MPG because it's my screencast. And I'm going to say, I want to find out how these vehicle classes differ in terms of their fuel efficiency. So I'm going to say V class by highway 08, and I always use a box plot and usually a coord flip if I want to look at differences in distributions. I'm also going to filter for uses for, actually I'm going to filter for, to make it easier to say, highway E is, or I'll say cities E must be 0. And did I write highway when I meant city? Yes, I did. I say in our non-electric cars, here's our distributions. 32 is going to be too many, but I might lump it in a second. But for starters, I'm going to say, here we go. I'm going to say V class is FCT reorder. It's from the 4cats package. V class by your city 08. It'll reorder it by the median, which suits me fine for box plots. It looks like standard pickup trucks, 2WD. I don't know. Pickup trucks. What is 2WD? What does WD mean? I literally have no idea. Two-wheel drive. Okay, that makes sense. Four-wheel drive, two-wheel drive. Okay, and yeah, your two-wheel drive standard pickup trucks are not looking like they're what you want driving. You want to drive your small station wagons if you want high efficiency, though even those have wide variation. This is way too many things to put on one box plot. One thing you can do when you have too many values is you do v-class fct lump v-class into 8 and then other. So now I can say here's my compact, subcompact, mid-size, other, and so on. All right, so now I can look at this in terms of distribution. I think there was something like drive, yes. So that's another one I could have tried a box plot on, would be to say just use my drive. For that, drive. All right, and what this shows is two-wheel drive, generally low efficient. See, it's so interesting to me, like front-wheel drive has some of the ones the highest efficiency. I would not know much about how to interpret this. Two-wheel drive, four-wheel, all-wheel drive. It's not even like a huge difference, except front-wheel drive definitely tends to have the highest efficiency. Note there's only among non-electric cars. Don't know what to do with that. I don't really have a good feel for how might drive affect the fuel efficiency. But I do know that we're going to care about some things like weight and the engine size. Here we go. Engine displacement is the engine volume. And we have our engine size. What I'm looking for is like the vehicle weight. Do you see? Because I don't see it yet. I'm looking for tons, kilograms. I'm looking for a lot of words that might affect weight. Vehicle mass. I'm not seeing it. Size. Only vehicle size. Class. Okay. If it's here, I'm missing it. It definitely was in the original MT Cars dataset. Remember, I could always be missing it. Like mass cylinders. Is there something like vehicle capacity for the number of seats? I'm going to keep reading through this. I know it's not interesting to watch me read a data dictionary, but it's nice. Hatchback, passenger, volume. What's that mean? Two volume dimensions. Okay. Okay. Transmission. Descriptor. PA city range for fuel type 2. Well, no, all right. I'm going to stop looking for size. I'm going to start with cylinders. I've got my select here. I wonder, how does cylinders affect? I don't know what I'm doing it here. I'm going to make this a third one. Cylinders, and whenever you have a numeric one, you need group equals cylinders. I'm not going to reorder it. Here we go. All right, generally, the fewer cylinders, I'm going to skip that coord flip. The more cylinders, the lower the efficiency. Makes a lot of sense. Larger engine and such. I imagine we're going to see something a little similar. On this one, I'm going to do a scatter plot, geom point. We're going to see something a little similar for engine displacement. Here we go. Yeah, I think we see something like this in empty cars. It's a common graph as you do something like vehicle weight or volume or engine volume versus I'm going to do expand limits y equals 0. Really like that. Should I do x equals 0? Why not? And yeah, so this is a classic visualization. Here we go. All right. I'm going to start doing a little bit of prediction. And let's say I want to predict the city. So my goal is going to be, this is really handy because I'm going to be able to do some should I do nonlinear regression? Yeah, I think I might do splines. Okay, there are a few approaches I can use to get nonlinear regression here, and we're gonna examine each of them. Our goal here is not to get the highest accuracy. Our goal here is to kind of explore the data and the particular relationships and understand how we might do prediction when the data is not exactly linear. All right, so goal, predict city fuel efficiency for non-electric cars. So I'm noting this because we have 360 electric cars and they are large outliers. We could use things like electricity to predict it, but at that point, it's for a single, I'm actually going to say it differently. I'm going to say single fuel efficiency cars. So what I'm going to do is say big EPA cars. I'm going to filter for fuel cost. Is it no, not fuel cost. What I meant to say was I'm going to predict this in terms of city 08. Yeah, I want only city MPG for only ones with 0. That is ones that don't have ones that don't have a secondary fuel source for single fuel cars. And then I wonder if I say city E0, does that change at all? Yes, a little bit. For single fuel, non-electric cars. Okay, I think I just want to start with that group for our prediction. I'm gonna throw something else in. I'm gonna do a little cross-validation. Hold out set. I'm gonna say, let me see, I'm going to call this non-electric cars, and I'm going to say, and I'll do, here's a trick if you want to sample n, sample frac 1. What this will do is rearrange all the rows in the data. So that's helpful if I was worried there was some ordering to it. And now I'm going to create a training set of non-electric cars, filter row number mod 5 equals 0. I'm going to leave out a holdout set of 20% of our cars, and we'll try and come back. Is not equal to 0. So the holdout set, technically I should have a training set, a test set, and a holdout set. I'm kind of being sloppy today because I'm just going to use only a few predictors, but I am going to keep a holdout set one that we hold out until the very end of our analysis. I'm probably going to hold out this one. I'm not going to be separately doing the training and testing along the way because we're not using very many predictors. I'll get more into that in a bit. Okay, so here's my training set, 32,000 cars. And as I noted before, if I want to predict the city efficiency, I could start with the displacement predicting the city fuel efficiency. Okay, basically the same graph I did here. Here we go. If I want to do a linear model on this, first I'm going to show that geographic, in terms of visualization. That would be geom smooth method equals LM. This isn't giving me a predictor, it's giving me a just a line. That's not an amazing predictor. We're going to return in a little bit to how we might be able to improve that that prediction. Just notice, like, it gets these really far off. It gets these. It's just not because this is not a linear trend. It's one that flattens out. This is not going to be a great method, but I'm still going to show it, and then we'll show how we improve upon it. So what I would do is say city 08 explained by displacement, where the data is our training set. All right, I'm going to pipe this to summary, and we see, hey, we got a significant p-value. Our slope is -2, 2.6, which means every extra, what's the unit of displacement? liters. Every extra liter in this engine is an extra, what was I saying? Yeah, every extra liter is, it will reduce the fuel efficiency by 2.6 miles mpg. Well, sounds reasonable. Creates a line, but it creates a line like this. That's a real mess. How can I tell it's a mess? Well, I could augment the original training set. Augment, I need to do library Broom. Broom is a package I originally created. It's now maintained by Alex Hayes, and it's a package for exploring models in the tidyverse. And in this case, augment is for adding extra variables to this data. To say, we have our original data, but then I also have the fitted values and the residuals, which are something really important. What are residuals? Residuals are the distance between this predicted line and the actual value. Now I can actually say plot display. I take this augmented data, plot displacement by .resid by the residuals, and show a geom point. I need an AS here. Now, ideally, we wouldn't see a shape of this residual curve. There wouldn't be any pattern in the residuals, and there definitely is. We are always getting the low, the small volume engine wrong by a lot. We're underestimating them, and we're overestimating the fuel efficiency of the larger engines. This is a terrible pattern to see on your residuals. We'd rather see like a much, kind of a much more random pattern, one that one that didn't show any trends. So this is a real problem, and you can really tell, that looking at this graph, no way is linear the right approach. What are some of our alternatives? One is what we call a natural cubic spline. A spline is a way to predict y from x, where we use it in a linear model, but where we know that the relationship is not actually linear. The way it does this, and I'm not going to go into the math here, is it splits that one linear predictor up into a couple of components that each get their own linear term. So the way I can do this is, I think it's library, is it splines? I think it's splines. Maybe it's library NS, we'll find out. And what I do is I add a degree of freedom. I say city08 is a natural spline on displacement with 2 degrees of freedom. Let's find out if I'm using this the right way. Nice, okay. Let me visualize what it actually looks like. I'm going to save this as augmented data. Let me show what it looks like. To show what it looks like, I would take my augmented data and plot displacement and city08, just like I've been graphing before, but also throw in geom line where the y is dot fitted, as opposed to y being the actual value. Here we go. I'm going to throw a color red and size is 3 on that. Really want to see that line. Oops, I want to put that on top. It's not bad, I just want to see it a little clearer. Size 3 is a little big. Let me throw this into size 2. Here we go. Notice that this has a new shape now. Instead of just being a straight line, it's taking on this this curved shape. So a spline allows a wider variation of curved shapes between our x and our y. And it's remarkable because we're still doing a linear model. We're still fitting a couple linear terms. In fact, I'm going to show, if we fit this model, what happened if I use Broom's tidy on it, is we actually have 2 terms for displacement. Instead of having one, we have 2 degrees of freedom controlled by the x-axis. And this ended up being a better predictor. How can we tell it's a better predictor? Well, I'm going to explore cubic splines a little bit using, that's actually going to be a really fun exploration, using Broom and the multiple models approach. You wouldn't do this if your only goal were to predict the efficiency. I'm doing it because I really like to explore models, and I like to show how splines work. So let's look at I think I've done this in another screencast, but I can't remember which. All right, let's take our training set and let's work with let's try some variations on this. All right, well, what I'm going to do, here we go. How am I going to do this? All right, I'm going to use one of my favorite functions, crossing. What I'm going to say is, no, I'm not actually going to do it a little bit differently. I'm going to say, let's try a natural cubic spline with a different number of degrees of freedom, 1 to 10. I put these in a tibble. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now I add a bunch of models to it. So how do I add these models? I would say on each item in this data frame, in these number of degrees of freedom, I'm going to fit a linear model of city 08 explained by displacement, with a natural cubic spline with some number of degrees of freedom. I forgot data equals dot. The dot would be what dot data equals training set. So the story here is I'm running the same line of code just like I have up here, except the number of degrees of freedom are changing each time. Every one of these ends up being a linear model. And I call these models. All right? I take my models, and now I can, 1 to 10 is too many. I'm going to do 1 to 6. Now I take these models, and I have a few ways I can unnest them. One of the first is I can say unnest. On every one of these, I'm going to I'm going to augment the model. Oh, right, it doesn't work that way anymore. I have to do augmented. This is going to be map model augment, and then I unnest augmented. Unnest has changed recently. Oh, look at all that. Right, I need data equals training set. Okay, let's see. What duplicated the name? I'm going to call this LM model for a bit. Yeah, I don't know model is one of our predictors. It's called model. Okay, so that's the reason that that caused a small problem with the unnesting. All right, I've created now 6 versions of this augmented training set stacked on top of each other. Why do I like that? Well, I like it because I can now visualize all 6 of them. I can say, here's my displacement city 08, my y fitted, but now I'm going to say the color is a factor of the number of degrees of freedom. Take 1 second. Taking a little longer than I expected. The reason it doesn't love it taking a while is that it's plotting these points on top of each other. I'm going to plot this. I'm plotting the original data right here. I'm plotting a geom line, one separately for each of these data sets. I'm going to see augmented, unnested is this. Here we go. What I'm doing is I'm trying to end up with 6 separate lines showing our 6 separate number of degrees of freedom in this spline. Here we go. Kind of like that. All right. What this is doing is showing, I'm actually going to tidy this up just a little bit because I kind of like this graph. And yeah, I do kind of like this graph. This is showing like when we added a second degree of freedom, we got a curve But once we added, like the more degrees of freedom we added, the more it could kind of cover this shape, this unusual shape between displacement and city 08. So the, yeah, so we had 2, it's like, it didn't look great, but once you added 6 degrees of freedom, we kind of like, we kind of see how we can predict this, and it's actually looking a lot better. With the engine volume, I'm gonna tidy this up. Engine volume liters, city MPG, color is number of degrees of freedom, and throw in and expand limits, x is 0, y is 0 for good measure. I wanted to show some of these variations. One thing it shows is there's never an engine under 1 liter, and yep, it shows these particular shapes. I just want to get that idea across of what I mean when I'm saying I'm fitting a nonlinear trend. This is one way to fit a nonlinear trend. It's generally considered a non-parametric method. We're not making assumptions about the shape here. We're just saying we know it's not linear. In fact, why did I do this augmented nested approach? Well, I'll show 2 advantages. One is I can create my earlier graph of the residuals. Where's my residual graph? Maybe I got rid of it. But I can say displacement by dot resid, geom point, and say facet wrap by the number of degrees of freedom. And now I can show that there were really there were strong residual patterns in the early ones, and they're going to get kind of weaker as the number of degrees of freedom increases. When I say weaker, I mean less prominent. Not much less prominent. Maybe a little? Nah, I think a little. But it's not perfect. Something to consider here is that we probably know something about the shape. We could also make a mathematical assumption around. But I did just want to show that. The other thing we can do is look at a measure of what was it? Yes. With these models, I could have also looked at did the model get better? How would I represent better necessarily? What if I used glance? Glance is a here you go on nest glanced. Glance. Oop. DF is one of our. I'm going to quickly rename the spline DF. DF is one of the results of a glance. That means it actually keeps track of the number of degrees of freedom. So I can actually plot. This will while augment added some data to the initial, something to the initial observations. Glance gets 1 observation per model. And here we can see, for example, the adjusted R squared or the AIC. I'm going to use adjusted, so AIC, which is a penalized term for the model, meaning it meant for goodness of fit. Penalized meaning it says, have we added too many degrees of freedom? So one thing I can do here is observe, I'm going to use adjusted R squared, which is one of my favorite measures of if we have a linear model of goodness of fit, and say we had actually a pretty good already, even with a linear model, we had a pretty good R squared. But if I use adjusted R squared and I say adjusted R squared, what this shows is adding a few degrees of freedom to that relationship made it much better, but it levels off. In fact, our adjusted R squared will start going down. If I make this go from not from 1 to 6, but 1 to 10, we're actually going to see that at some point we add too much, we add unnecessary complexity. In an ideal world, we would even cross-validate this, but I'm not quite going to bother with that. You can use, I think the GAM package. There are a few packages that would allow us to fit these nonlinear models, and then it looks like it could get better, but I think it's mostly overfitting. Mostly you get a benefit from your first 4 degrees of freedom or so. All right, so that's what we can see in terms of like adding degrees of freedom to our fit. All right, that's some thoughts in terms of splines with predicting efficiency by the volume. I'm going to return for a bit to the data. I've got a couple choices. Am I going to try fitting? No. I am going to try adding a couple terms to the model. All right. What I'm going to do is say I was trying to decide if I wanted to try other ways of predicting the relationship, but for now I'm okay with summary. For now I'm okay with using my displaced term, my linear model. I'm going to say let's add 4 degrees of freedom. It looks like it kind of levels off after that. That's a super hand-wavy way of doing it. I could have used cross-validation to find the number of degrees of freedom. I like it, and I think it's pretty conservative to say we use 4 degrees of freedom. I'm also going to add in, how about the number of cylinders? That also has a significant effect. That is statistically significant. More cylinders, we saw in an earlier box plot, more cylinders does mean a lower fuel efficiency. But this may also have our adjusted R squared went up by a little. This could also have a nonlinear trend. How many? I don't know. Is that a little bit? And it goes up a little. I'm not going to push this one. Maybe, I don't know, 3 degrees of freedom. I'm being very casual here. But the story is what I'm doing is I'm adding terms in, nonlinear terms into the regression. I'm also making my residual standard error going down. I've got a holdout set if at the end I want to see how we actually did. But this is how I combined volume and cylinders, and each to remind ourselves, why did I say cylinders had a nonlinear effect? It's because it kind of has this flattening pattern. Both of these have this kind of asymptotic or maybe hyperbolic pattern. I could try doing the fit on it probably would make sense to do the fit on functions rather than on splines. Should I try that? Do I even remember how what equations would describe this, or am I going to blank out on that? I'm going to leave it like this. I think I'm going to leave it like this for now. All right. This would be one approach where I'm showing the summary. And if I wanted to say, here's something useful. There's really no way to interpret these coefficients, the number of cylinders, the volume. There's really no way to say, like, oh, this p-value is significant. What does that mean? What I would instead do is use ANOVA. And ANOVA will tell me whether the entire term, the entire displacement, or the entire cylinders explains more variation than you'd expect by chance. An ANOVA object can be tidied, and there I get like the sum of squared, the mean of squared. This is useful because I can say what percentage of variation does each of these explain. Here it's showing like percent of variation is going to be sum of squares divided by the sum of squares. So it says 62% of the variation is explained by the engine volume, very little by the number of cylinders. Okay, why would that be the case? Aha, and I have a good suspicion as to why. I believe that displacement and cylinders are highly collinear, that they're highly correlated. And so much so that it's probably a mistake to even work with the number of cylinders at all. I should have thought of that a little bit earlier. But what we can do is actually, for starters, I can graph our training set cylinders by displacement and do a group. We're going to see that, the more cylinders, the larger the volume of the engine. So that means these, it's probably not worth combining these two terms together. they're going to be so correlated because cylinders are in the engine, so probably don't want to use that at all. Which of them, if I have to use one of them, which of them would I use? I'm not even going to bother with that. I'm going to look at some. I'm going to keep adding in variables that I might be interested in. I want to add. Let's see. Vehicle size class. Nah, I might come back to that. I've been doing some I want to answer some more exploratory questions. Sorry, maybe my head's not in the prediction game. I'm not excited enough about predicting the fuel efficiency. I want to know have cars been getting more efficient over time? Do I have a distribution here? Stay in the training set. Do we have a distribution of years here, or are they all from, like, say, the same couple of years? I can find out by creating a histogram. Oh, that's great. These cars are, I'm going to throw in a bin width equals 1, have every bar be 1 year. These are not quite evenly, but not that far from evenly distributed across about 1984 to 2019, current year. All right, so that's great. And what that means is I could say group by year. I could start and just say have cars been getting more efficient. This is confounded with every other possible factor, but I'm going to say group by year. No, I'm going to do ggplot year city E box plot and group equals year. Always with the numeric x-axis you need. I said city E, I meant city 08, the city fuel efficiency. Here we go. And it looks like cars have been getting a little more efficient in the last couple of years. This is only among non-electric cars. These box plot has way too many outliers, so I'm going to start with, I'm going to make this a geom point and do geom lowest. Oh, nope, geom smooth. Lowest is another method for looking at nonlinear trends. Lowest would say, get rid of group equals year. Lowest would say, stands for local, I forgot all the terms here, but it's a local regression where it basically fits a regression that slides along in a window. Ooh, we have too many observations. It's taking a minute. But we're going to see if there's a general trend here. And in the meantime, we're going to try an easier approach to seeing whether there's a trend, which is the group by year, summarize average efficiency is mean of city 08, and plot that. Wow, that lowest has taken a long time. Way too long. I don't want a Terminator. One of the things that I want to look at once it's finished running, one of the things that I'm going to want to look at is copy the whole file just in case everything crashes. One of the things that I want to look at is that because look at how much faster that was. Average efficiency goes up by a solid amount around 2010. I think there were some fuel efficiency laws passed here around early Obama administration, but I don't know a lot about it. I am going to expand the limits. Say y has to go down to 0, otherwise it looks more dramatic than it is. But that's actually pretty cool. Average fuel efficiency increased after starting around 2009, and it's leveled off a little bit since around 2013. But is that because cars have been getting more efficient, or is it because we've been changing? Let's see, I already say this. Yeah, is this because we've been is this based on other changes in terms of our, say, engine size, kinds of, or the models? One way we can answer this question is to take our V class, to say FCT lump V class into 8, or should I do even fewer? All right, and then say average efficiency color equals V class. To ask, has the efficiency been happening And yes, it looks like it has been happening within vehicle types, not just in terms of, say, the distribution. Notice that we don't have any standard pickup trucks since the late 1990s. That's interesting. But yeah, we're seeing, I think it doesn't show, yeah, I think a lot of the improvement comes in mid-size, wow, a lot of the improvement comes in mid-size cars, but we also see in large cars. Where we don't see it is in subcompact cars. There probably was no real room for improvement. We can see they already were pretty efficient. But wow, mid-size and compact cars got way more efficient. Here we go. I'm going to make it slightly less noisy. I'm going to round within each pair of years. How do I do that? I do, I'm going to remember myself, 2 times year mod 2. Not year mod 2. Year divided by 2 with a floor. Yeah. So what this does is round to the nearest pair of years. I actually like that graph more. It's kind of more of a trend here. And yeah, this is showing, I've got our summarized efficiency and time. I've got our trends here. We can see our increase around 2010. What else am I going to do? Yeah, I'm actually, besides average efficiency, I would be interested in, has the engine size been changing? Average number of cylinders. No, the engine size been basically staying constant. Ooh, it dropped for large cars. That could be part of, and it dropped for mid-sized cars. And were those the two where we saw improvements? Yes. Okay, so that actually does suggest that's average cylinders. I'm also going to do, now that I know I'm doing the average for a lot of things, I'm going to summarize at vars, and it's city 08, cylinders, displacement, engine, I restarted the R session. Oops. That was a mistake. I really didn't mean to restart the R session. I hit a, a keyboard shortcut that did that. Uh-oh. Oh no. I want to finish up. Well, what I was trying to say here is that it looks like a large part of the reason is they've been pushing towards smaller engines, that we see a big increase in the efficiency of large cars and mid-sized cars is that they've been pushing for for smaller engines. There are a lot of reasons we could imagine that happening. I bet we saw this thing about the Guzzler tax. Wow, this is rough. I am going to reopen in a brand new R session because it's still restarting. I'm going to open in a brand new R session, open up my file. That's embarrassing. And save it. Okay, I'm going to work with this one instead and say go, reload up my data. Summarize that, take the average of each of these. I'm actually going to add a column called Guzzler equals. Guzzler is either is either equal to, it says if it's G or T, it's subject to the gas guzzler tax, so I'm going to say G and T. And we create my training set. I didn't have time to look at the holdout set. So I'm always figuring out what I'm interested in graphing here. And I'm taking the mean of each of these. So what I'm saying is, And I'll take the mean of Guzzler as well. So this shows what fraction of cars are Guzzlers. Count. What was Guzzler in the original? Oh, It said if it's G or T. Well, it looked like it was true or false in this case, so I actually made a mistake by recreating it here. And say, but I should say not is an A. Guzzler. Here we go. I want to know what fraction of cars are Guzzlers over time. And that might show where the, so now I can show my average efficiency, which is now called City 08. I can show my average number of cylinders, or maybe I've already looked at that. Let me show the average displacement. Engine sizes got a little smaller starting around 08. And I bet, though I'm going to have to find out now, I bet if I look at the fraction of cars that are Guzzler, there's a change around. Oh yeah, look at that. It's like it just went to 0. When did that law come into effect? I'm also going to say, some of these are probably like, see, it looks like two-seaters used to be really inefficient. A large fraction of them were Guzzlers. And then, yeah, there have been none of them since 2004. If I search gas Guzzler tax, when was it introduced? In the United States. 1978. Well, for whatever reason, it looks like kind of a few of them did happen in the early 2000s, but then it really none have been produced since 2004. Okay, that's interesting. I also see that the engine size shrinking, especially mid-size and large cars. All right, so the lesson we have here is engine size started shrinking around 2009. Probably regulatory pressure. I just don't have the context to be sure. And this was accompanied, and this led to, I'll say, especially in large and mid-size cars, and this led to an increase in fuel. I'll note city fuel efficiency. All right. So I've learned some things from this data. All right, so what did we do today? I showed how I jumped into a large data set, browsed through a lot of the variables, picked a few that I was interested in. I started exploring how I would do a prediction, and in particular a nonlinear prediction, where I saw this, created this trend I really like. I think I looked, maybe it was birds in Chicago. I don't remember when I looked before at and I created this exploration where we learned about highway versus city. I got the hypothesis that the difference was around whether they use electricity, and that seemed to be correct. We looked for a little bit at nonlinear trends and how we might use the multiple models framework to explore them and show how the number of degrees of freedom. I didn't create this one yet. Forgot library room. And we showed how that happens sometimes with a visualization, just when I resize it. That's better. When we show how adding more and more degrees of freedom changes the shape of the line that we're predicting, and it lets it really kind of adjust to the data a little bit more, and how that might affect the adjusted R squared. So let's look at nonlinear at the splines for nonlinear models. Then finally we take a look at the question of how it's been changing over time, and got to this idea that it had shown an increase around 2009 to 2013, 14 across a couple different types of cars. All right, so that was a fun exploration of car fuel economy. Another really great Tidy Tuesday data set. I hope you had fun. I certainly did. I'll see you next time.